I'm Henri Díemoz. I work at the Environmental Protection Agency of the Aosta Valley in Italy. And I was asked by the organizer to give a short talk about nitrogen dioxide measurements with the brewer. And this is a very basic presentation. In the next days, I will give a more detailed talk about recent advances about NO2 measurements. So just a short introduction for those who are not familiar with nitrogen dioxide. It is a key component of our atmosphere, both in the stratosphere and in the troposphere. In the stratosphere, it is a catalyst of the ozone destruction, and it also moderates the ozone loss at lower altitudes. In the troposphere, it plays an important role in the photochemical smog, in the acid rain, and it is also involved in the radiative forcing, being an absorber in the UVA and visible range, which allows us to retrieve the nitrogen dioxide vertical column with the brewer. The Mark IV brewer was expressly designed for retrieving the nitrogen dioxide in the visible. Here, there is a highly structured absorption band of nitrogen dioxide, which allows good retrieval of this gas. But in 2006, Alexander, who's here, developed a new method to retrieve the nitrogen dioxide with Mark III brewers in the UVA range. This is probably not the best wavelength range because, you see, the absorption is less structured than in the visible. But it demonstrated that nitrogen dioxide retrieval are good as well. So Mark IV brewer can retrieve nitrogen dioxide in this range, 431, 453. The first slit, the mercury slit, is not used in the traditional algorithm. You have in a dual brewer the N2 and O3 command that makes you switch between the third order of diffraction of the grating, where the ozone is retrieved, to the second order of the diffraction. Here is the grating equation. So for a fixed micrometer step of the grating, you have a constant product between the diffraction order and the wavelength. So both resolution and wavelength are multiplied by these factors, 3/2, then the UV wavelength and resolution. The original algorithm for Mark IV brewers was developed by Kerr in the late 80s, and it is the only algorithm which is currently in the software, in the brewer operating software. There are some updates by David Barton and me, which are not currently implemented in the software. Mark III brewers can retrieve nitrogen dioxide in this range, in the UVA, if I'm not wrong. And the reference paper is the paper by Alexander. And there is a DN routine which retrieves the nitrogen dioxide in this range. But as far as I know, it doesn't provide any results you have to process by your own to get some results. Nitrogen dioxide in the atmosphere has very low column densities of the order of 0.1 or 1 Dobson unit. So an accurate characterization of your own instrument is fundamental to isolate the contribution by your instruments and the environmental influence of nitrogen dioxide. Those measurements can be performed in 3 different geometries. You can directly look to the sun through the direct sun measurements. The air mass calculation is very simple in these geometries, straightforward. But the problem is that the path of the sunbeam is very short, so you have high noise. And in the zenith geometries, both in the parallel polarization with respect to the scattering plane and the perpendicular polarization to the scattering plane, you have a higher signal from the NO2 because the path in the atmosphere is longer. Traditionally, the parallel polarization was preferred because in this polarization, all skies behave like a cloudy sky. So clouds don't perturb the measurements so much. But David Barton discovered that this polarization is strongly influenced by the ring effect and also the number of photons reaching the optics in the polarization is lower. So now the zenith sky routine puts your tracker perpendicularly to the sun to get measurements at the perpendicular polarization. The algorithm is very similar to the one for ozone. You have Rayleigh, NO2 absorption, and ozone absorption, aerosol extinction, a constant term, and you find some weightings to cancel out the contribution by the Rayleigh scattering, the ozone absorption, aerosol, and a constant term. And you only remain with the nitrogen dioxide term, the extraterrestrial term, and the measured intensity, the linear combination of the measured intensities. And similarly to the ozone measurements, you can even correct the ETC constants using the ratio obtained with the lamp. It is called F ratio. So what's wrong with the standard nitrogen dioxide algorithm? If you just pick up the data from your B or D file, you probably will get disappointed because you have great overestimation by the traditional algorithm for Mark IV instruments. You will notice random deviations which are probably due to the oxygen dimer, the water vapor, and the ring effect, and wavelength misalignment. The Brewer is very sensitive to wavelength misalignments for nitrogen dioxide measurements. You will also have high noise, depending on both the algorithm and the instrumental setting, the wavelengths. And most of all, there is no calibration service by EOS or Kipenzone for nitrogen dioxide measurement, as far as I know. So you will probably have wrong ETC constants. And this is the effect of wrong extraterrestrial constants. You may see each day an inverse U shape or a U shape, depending on the air mass, which is a clear sign of wrong calibration. You also see that those values are too high for the Aosta site, which is a semi-rural site. But in the last few years, there have been some advances. A much better agreement was reached between the Brewer and the other instruments. The interferences are reduced, and the noise too. And I made a successful Langley plot in Isagna of nitrogen dioxide. So if you want to give it a try, you can test those weightings. These are calculated for my own Brewer, so they will probably not work for yours. But you can test it with that differential cross section. But you still need the ETC, so you can go with your own Brewer to Isagna. This is mine Brewer, the assembled. Or maybe you can also use statistical methods, like the one described in this paper. You can reprocess the series and then find an ETC that is the best compromise for the series. And once your Brewer is characterized and calibrated, you can get very nice results. For example, this is a plot illustrating the results, the retrieval by the Brewer, Dobson units of the full atmosphere. and the in situ measurements, air quality measurements, and you see nice correlation. These are monthly means, nice correlation between those two measurements. You can also see the weekly cycle with statistical differences between the weekends, Saturday and Sunday days, and the weekdays due to the use of cars and the factories. And now satellite and Brewer agree much better. You can see the same scale, even though the Brewer has a completely different seasonality than satellites. Okay, that's all. For a more detailed talk, you can come to the Congress in the next days, Friday. Okay. Thank you.